So today's topic about binary arithmetics. This related to digital logic. I think some of you might be familiar with this. It's depending on your curriculum if there is a digital logic circuit in your curriculum. So the problems that I recommend after today's lecture from 12:11 until 12:20. And remember, the last quiz will be in this Friday. There is a note sheet allowed. It will be in lecture 33 and 34, which is basically op-amps and digital logic. So these two lectures will be included in that quiz. Again, there is a note sheet. It can be either one side or two sides, it doesn't matter, but only one sheet, single sheet. Handwritten, of course. You can write whatever you want on this sheet. Then you expect to see op-amps again, or binary arithmetics. So the digital system, what do you mean by these numbers? What these systems? Most likely when we talk about the computers or the machine language, they understand only on-off or 0 and 1, which is called binary systems. And they are basically, the computer revolution happens from large scale to small scale, as we see right now, because of the transistor. And the transistor will act as switch, sometimes as fast switch. The faster the switching, or the faster switch of the transistor, which is the faster system. So let's recall sometimes in the early of 2000, we heard about the system that can handle 8 bits. Then after that, we hear that some of you might be familiar or might hear about this. So computer system was working on 8-bit system. Then after that, 16 bits. Then we said, oh, we can make it 32 bits. And right now we see 64. So right now we're still using 32 and 64. So sometimes when you have your, for example, Windows, then you can see like my Windows operating system is based on 64 bits or based on 32 bits. What does this mean? So basically we can say it's the number of bits, since it's binary, it can be either 0 or 1. So the number of bits is 2. Then 2 power number of bits that we are using, so the computer that can handle. So for example, it can be 2 power 16, 2 power 32, 2 power 64. So that's how these systems are working, or that's how we can say that 64 system is capable of handling more stuff or more complexity, can handle more than 32 and so on. So the numbers, as we used to know in our life, which is the decimal, 0 and 9, from 0 to 9. So 0 to 9, then 10, and so on. So here 0 to 9, 10, 11, and so on, 20. So basically, the digits is, it can be from 0 to 9, each digits. That's how we count in our daily life. But the computer, again, since it's based on transistors, which is based on switches, it can only understand 0 and 1. How can we deal with this? We have binary system. 0 means switches off, 1 means switches on. So light on, light off, light on, light off. So how we can count using 0 and 1? So we can start counting, it's like when we talk about decimal, after 9 we go 10 and so on. But here we cannot say 0, 1, 2. We will say 0, 1, 10, 11, 100, 101, 110, 111, and so on. So 1, 0, 0, 0. So that's, if we want to count, we have only 1 and 0. 1, 0, 11, 100, 101, 110, and so on. So in decimal, we used to say 1 plus 1 equal 2. In binary, 1 plus 1, we cannot say 2. We will go to the next digits. So it's going to be 0, and by hand 1 here, carry 1, then it will be 10. And so on. There is also another system based on hexadecimal. Hexadecimal based on 16 digits. So which is basically 0 to 9. Then now we can represent 10 since we don't have enough numbers or symbols on numbers, and we will use the alphabets. So we will use A, B, C, D, E, F. So A will stand for 10, B stands for 11, C 12, D 13, E 14, and F 15. So basically the range, the numbers that we know from 0 to 15 based on our knowledge, which is our reference is the decimal. So why our reference is decimal? Who knows? Like when they created the system, they said like our reference is decimal. But there are many references, especially in programming, to use decimal, binary, hexadecimal, and so on. So hexadecimal based on 16. Then in hexadecimal we can have more numbers with smaller quantities of digits. And there is another number called octal, which is basically from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7, then 10. We will not say go to 8. 10, 11, 12, 13, 14, 15, 16, then 17, then we will go to 20. We cannot go, any digit cannot be higher than 7. So these 4 bases that we expect to discuss today. So there are 2 numerical notation, which is based on the position and based on polynomial. Basically, when we look at that any digits or at any quantity, it's depending on the position. Of course, when I look, for example, at 100, like this, the position of 0 matters here. Here, 0, it works, like it will change the number. But if I change the position 0 to the other side, of course, it's different. Which is basically everyone knows this. Now, I'm going to discuss about the hexadecimal. Hexadecimal, again, it's count from 0 until, can handle from 0 until F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, F, then 10, 11, 12. So you see now, the 10 in hexadecimal is no longer equal to the 10 that we know in decimal. And it's no longer equal, it does not equal to the 10 in octal. It does not equal to the 10 in binary. So the 10 in hexadecimal, sometimes the hexadecimal we denoted it by 16, here is the base 16, does not equal to the 10 in base decimal. It does not equal to the 10 in base binary. It does not equal to the 10 in base octal. How? The 10 in hexadecimal is actually 1. Let's consider this in decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's equal actually to 16. The 10, this is in our reference in decimal. Our reference, which is decimal, equal to 16. That's the number that we know. That makes sense for us. 10 in decimal, it's the same as we know, 10. 10 in binary is actually, the binary we counted, 0, 1, 10. So it's actually 3. 10 in octal is actually 8. So we see, even though those are all 10s, but they are different than what we know. Now, how can we figure it out? How can we calculate this? Now, I will discuss this. So you don't need to count on your fingers and say A, B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, F, G, then 10. There is no G, E, F, then 10. So we will see this now. So starting from now, we will donate 16. This means hexadecimal. 10 means decimal. 2 means binary. 8 means octal. So the position notation, when we want to convert any number from binary or from to base to the number that we know, which is the decimal. So we call it the polynomial notation or the position notation, which is basically we will say, let me write it here. 234 base 10. The location of this one, we'll call it, let's call it B0. This is bit 1. This is bit 2. So basically what I need to say, and here is the base. Let me call the base R. I will say that B0 times base power 0 plus P1 times base R1 plus B2 times base power R2 and so on. Then this number will be 4, B0 is 4 times base, which is 10 power 0, plus here is 3 times base, which is R1. The base is 10 power 1, plus here is 2, plus base 10 power 2. Then 10 power 0, 4, it will be 4 plus 30 plus 200, which is 234. It's the same, the number that we know. Basically, I'm converting any number from any base to the decimal. So here to convert to decimal. Convert any system to decimal. Now, how about the binary? I want to convert 10101 base 2 to the decimal. So 10101, I don't know the quantity or the meaning. What does this mean? How can I convert this to a number that we know, or to convert it to decimal? Then we will say this is base 0, this is base 1, this is base 2, this is base 3, here is base 4. And this is bits, and the base here are equal to. So basically it's going to be B0 times R power 0 plus B1 times R power 1 plus B2 times R power 2 plus B3 times R power 3 plus B4 times R power 4. So this can be applied for any number. Now let's substitute. B0 equal to 1. The base is 2, R equal to 2, then power 0. Plus B1 equal to 0, plus 2 power 1, plus B1 equal to 1, plus 2 power 2, plus B3 equal to 0, plus 2 power 3, plus B4 equal to 1, times 2 power 4. Then substitute here. 1 times 2 power 0, 1, plus here is 0. 1 times 2 power 2, this is 4. 0 times anything, 0. Then 1 times 2 power 4, here is 2 power 4. Let me say here is 2, 4, 8, 16. Then the answer will be 16 plus 4, 20, plus 1, 21. Then we will say 10101 in binary, it's actually equal to 21. That's how we figure it out. Then we can apply this to any number that we know. Okay, clear? So basically, when we have any number, any decimal, or any number that I need to convert it to decimal, convert any number to decimal, then we will make sure that weights label the bits. Here it's called as n, I call them as b, then it should be fine. How about if there is in the notation let me write example. Converts the opposite, let's make it. Converts binary, or actually, I'm sorry, decimal to binary. How about the opposites? Here, I already, in the past here, we already talked about how to convert binary to decimal. Or it can be octal, hexadecimal, and so on. How about the opposite? Converts decimal to binary. basically, we need to convert, or when we look at any number, make sure that you will divide it by 2 each time. So what we will have the quotient, remainder, and here is the base. After that, take the quotient, divided by 2, then it's going to be, we will get another quotient, remainder, then here's the base. Then keep going. Quotient 1, 2, remainder 2 over the base, until reaching a point that the quotient will be 0. Then the number go up. You will start from here, Q2, Q1, Q0, and so on. Base, for example, depending on your base. If it's the base 2, if it's base 8, if it's base 16. So let's look at an example to make sure that we understand it very well. Let's start with 234, which is base 10, this means decimal. I need to convert it to binary. Now here my base is equal to 2 because it's binary. Now 234 divided by 2. The answer is going to be 117. There is no remainder. So what should I substitute in the remainder? 0, base 2. Now this is the quotients. Take this, 117 divided by 2. It's going to be 58, and the remainder is 1, so 58 1/2. Then take 58 divided by 2. It's going to be 29, and there is no remainder, so it is 0. Then take the 29 divided by 2. It's going to be 14 1/2. Take the 14 divided by 2. It's going to be 7, and there is no remainder. Then take the 7 divided by 2. It's going to be 3 1/2. Take the 3 divided by 2. It's going to be 1 1/2. Take the 1 divided by 2. It's going to be 1/2, and the remainder is the quotient is 0. So since we reached the 0, stop here. Stop. We reached the 0. Now look at these values, which are the remainders. Then start up. So it's going to be 1, 1, 1, 0, 1, 0, 1, 0, base 2. That's it. So make sure, just apply the procedure. Then we will say this number is actually this number in binary. This number in decimal equals to this in binary. Clear? Any questions? Now, how about sometimes write in, take some more examples to make sure that we understand it very well. Okay, let's try another example. Now we should be able to know how to make the conversion from binary to decimal and the vice versa, decimal to binary. So let's assume that we have 1, 0, 0, 1, 1. It's in binary, and I need to convert it to hexadecimal, to decimal. Basically what we need to do, this is bit 0, bit 1, bit 2, bit 3, bit 4. Now I assume everyone knows how to do it, right? How we do it? Equals to what? B0 times 2 power 0 plus B1 times 2 power 1 plus B2 times 2 power 2 plus b3 times 2 power 3 plus b4 times 2 power 4. Now substitute the numbers. b0 equal to 1 times 2 power 0, which is 1, plus b2 equals to 1 times 2 power 2, 2. b3 equal to 0 times 2 power 2 equal 4, plus b3 equals to 0 times 2 power 3 equal 8, plus b4 equal 1 times 2 power 4 equals 16. So as a result, it's going to be 1 plus 2 plus 16. Yes, this is going to be 19. And here it's in decimal, so I will put the base as 10. Understood? Now let's go back to the notes. When we label the bits as B0, no matter if you call it B0 or A0, make sure that this B0 is called, or the A0 is called least significant bits, LSB, and the AN is called most significant bit, MSB. Least significant and most significant, which means least significant, this one has the lowest weights, 2 power 0, which is equal to 1. This is the lowest weights. While the most significant bits, for example, 2 power 4, which is the highest weights. So this bit, which makes sense for us, or the highest weight, because it's the largest bits that we know. So based on here, we will say least significant bits is actually B0 here equal to 1, and most significant bits is actually B4, because the highest is B4, then it's equal to 1 here. So just for your information, that's what's LSB mean, what's MSB mean, least significant bit and most significant bit. Now let's take another example. We need to convert 54 from decimal to binary. How can we convert it? Basically, we will say that 54 divided by 2, it's going to be 27. The remainder is 0. Then 27 divided by 2 is equal to 13. The remainder is 1. 13 divided by 2 is 6. The remainder is 1. 6 divided by 2 is 3. The remainder is 0. 3 divided by 2 is 1/2. The remainder is 1. 1 divided by 2 is 0. And here is 1/2. Since we reached the 0, then let's stop. Stop here. We reached 0. Then start from up to down to count these numbers. Then it's going to be here 1, 1, 0, 1, 1, 0. This is in binary. Clear? Yes.
Will binary always have base 2? Is that like a...
Yes, yeah. The meaning or the definition of the binary, which is by or 2 digits, 0 and 1. Okay, any questions? Now, how about if we have decimal points? How can we treat this?
Where did your last 0 come from on the... It looks like you ended with 1. Oh, you went from the bottom up. Is that what you did?
Yes, start from the bottom to the top. So 1, 1, 0, 1, 1, 0. 1, 1, 0, 1, 1, 0. Now, how about if we have decimal points? How can we treat it, the problem? Let's assume that I have, for example, B4, B3, B2, B1, B0, then decimal points, B -1, B -2, then here is base, for example, base R or something like that. So basically, when I want to convert this, if I want to convert it to decimal, it's going to be B4 times R, which is the base, power 4, plus B3 times R power 3, plus B2 times R power 2, plus B1 times R power 1, plus B0 times R power 0. Now, after the decimal, I start counting them as negative. So it's going to be negative 1 times r power negative 1 plus b negative 2 times r power negative 2. That's when we have after the decimal points. Now, sometimes it's not called decimal point. It can be called, actually I forgot, but the decimal point is related to the decimal numbers. I think it's called radix points, something like that. I'm not sure. But after the point here, the weights are different. Now, we need to make sure that we make the power negative. Then start counting negative 1, negative 2, and so on. This is example. We have this point. So the first step when we see this question, make sure that what's my base, what's the base that I need to convert. Then we will see that here, this is base 1, this is base 0, this is the points. Then start count negative here. This is b negative 1, this is b negative 2, and this is b negative 3. Okay? Why I have negative after this decimal points, negative 1, negative 2, negative 3. And here after before, start from 0, 1, and so on. Then it's going to be how the base that I have, 2. So it's going to be equal b1 times 2 power 1 plus b0 times 2 power 0 plus b negative 1 times 2 power negative 1 plus b negative 2 times 2 power negative 2 plus b negative 3 times 2 negative 3. So it will be b1 equals to 1. 1 times 2 power 1, which is 2. b0 is 1. So b0 is 1 and 2 power 0 is 1. Then plus b negative 1 is 0 times 2 power negative 1, which is 1/2. Plus b negative 1, which is 1 times 2 power negative 2, which is 1/4. Plus b negative 3, which is 1 times 2 power negative 3, which is 1/8. So it's going to be 2 plus 1 plus 1/4 plus 1/8. So 1/4 is 0.25, or we can say it's 2/8 plus 1/8, 3/8, so it's going to be 3/8. Or you can simplify more, 3/8, and you can figure it out. So this is in base 10. So this number equals to this number. So what's 3/8?
1.375.
375. Oh, thank you. Any questions? So that's how we make the conversion if there is decimal point or if there is no decimal point related to it. Another example, if we have let me say 111 base 2, I need to convert this to decimal. Basically, again, starts from here, b0, b1, b2. This is b negative 1, b negative 2. So it's going to be, we don't need to make justification. You can just substitute it directly by saying 1 times 2 power 2 plus 0 times 2 power 0 plus power 1 plus 0 times 2 power 0 plus 1 times 2 power negative 1 plus 1 times 2 power negative 2. So as a result, it's going to be 2 power 2, 4. So it's going to be 4 plus 0 plus 1/2 plus 1/4. So then it's going to be 4.75. Any questions? Here I just solve it without writing the formula, so you don't need to justify your answer. You just make the conversion, and that's it. So especially when you see this in the quizzes or in the exam, all of the stuff that related to the binary or conversion, it will be graded as final answer. Okay, now, how about conversion from hexadecimal to binary or to binary, or convert hexadecimal to the decimal? How can we make this conversion? The best thing when we deal with hexadecimal, hexadecimal means the numbers from 0, which is the base 16, from 0 to f. So f is actually equivalent to 15. Then how can we make this conversion? Basically, when you have hexadecimal, I will the shortcut hexa, convert this to binary first, then from binary go to decimal. How about if the opposite? I have decimal and I want to convert it to hexa, convert the decimal to binary, then binary to hexadecimal. So now we know how to convert decimal to binary or binary to decimal. The next step we need to worry about how to make the other parts. So we already discussed this. We know how to do this. How about doing this? Hexa to binary. This table summarizes everything. I encourage you to write down this table in your note sheets in the quizzes and the final exam, because you will need it. I will not give it to you in the exam, and you will need it in the final and in the quiz. So this table, basically what you need to do when you have any hexadecimal, you need to convert, or any binary to hexadecimal or the vice versa. Look at these numbers, group each 4 digits, and this is the equivalent in hexa. The equivalent in hexa. So let's look at this number. You need to group each 4. Start from the decimal points. Let's group each 4. This is 1, 2, 3, 4. We group them together. Now, this is 1. How about the other 3? What do you think? I need to group each 4. I group this 4. How about this one? How can I group the other? It has only 1.
You put zeros in front of it?
Yes, right. Keep it zeros. How about this number? Start from the decimal point. Now group each 4. 1, 2, 3, 4. Now here, 1, 2, 3, 4. How about if, for example, I have less than 4, then you will put zeros also here. Now, look at the table. 0, 0, 0, 1. This is, I need to convert this to hexadecimal. 0, 0, 0, 1, this is equivalent to 1. So this will be 1. 1, 0, 1, 0, 1, 0, 1, 0, equivalent to A. This is A. The decimal point will be as is. 1, 1, 0, 1. 1, 1, 0, 1 equivalent to D. 1, 1, 0, 1 equivalent to D. 1, 1, 0, 1, it's also equivalent to D. So as a result, it will equal to 1A points D, D. This is the hexadecimal. Clear? Any questions? Now, let's go back one step to the example that we discussed, that we found here. We already converted 54 from decimal to binary. How about I want to convert it to hexadecimal? Basically, let me write it here, 1, 1, 0, 1, 1, 0. Let's group each 4. 1, 2, 3, 4. Here we have 1, 2. How about the others? Zeros. So 0, 0, 1, 1 equivalent to what? 0, 0, 1, 1 equivalent to 3. 0, 1, 1, 0. Let's see here. 0, 1, 1, 0 equivalent to 6. So the answer will be 36 in hexadecimal. So you see, the number 54 equal to 36. How? This is in binary, it is in decimal, this is in hexadecimal. Okay, clear? Any questions? How about another example? Converts 11a point B to binary. This is base 16. Now how about doing the opposites? 1, 1A point B. Let's start with the first one. 1 in hexadecimal equivalent to 3 zeros 1. So what you need to write? 0, 0, 0, 1. The other one equivalent to 3 zeros and 1. 0, 0, 0, 1. A is equivalent to 1, 0, 1, 0. Then write it as 1, 0, 1, 0. The decimal points, what it as is B equivalent to 1011. 1011. So as a result, it will be 0001, 0001, 1010.1011. This is in binary. Sometimes you can remove these zeros because the zeros does not make sense. You can keep them or you can remove them. That's fine. Okay, clear? So now we know how to make the conversion from binary to hexa and the vice versa. How about doing octal? In octal, I can add this in this table. You need to group each tree. So for 0, 0, 0, 0, 1, 0, 0, 1, 2, 0, 1, 0, 3, 0, 1, 1, 4, 1, 0, 0, 5, 1, 0, 1, 6, 1, 1, 0, 7, 1, 1, 1. So how to make the conversion from octal to decimal? Basically, we can follow this. Here I have octal. Here I have hexadecimal. Then basically convert this to binary or the vice versa. Then to decimal. For octal, in octal, group each tree. In hexa, group each 4. So let's go back to this number and convert this to octal. So 0, 0, this number is actually 11010.1101101. This is binary. I need to convert this to octal. How to convert it? Basically, group each tree. Start here, 1, 2, 3. Here is 1, 2, and the third one will be assumed as 0. Here, the decimal point will be as is, 1, 2, 3, 1, 2, 3, 1, 2, and the missing will be 0. Every time, the missing digit will be 0. So, 0, 1, 1, let's go here to the table. 0, 1, 1 equivalent to 3. 0, 1, 0, go to the table. 0, 1, 0 equivalent to 2. Decimal point will be as is, 1, 1, 0, 1, 1, 0 equivalent to 6. 1, 1, 1, go to the table. 1, 1, 1 equivalent to 7. 0, 1, 0, 0, 1, 0 equivalent to 2. So as a result, 32.672. Yes?
Does it matter from what side of the number you start your grouping from? It looks like you started here from the left side, and in a previous one when you were doing hexadecimal, you started from the right side.
Here, we need to start from the decimal point. Look at the decimal points. Then you will start this side and this side.
Okay.
So here, start from the left, and in this point, start from the right.
Okay. And that's for all of them?
For all of them, yes. For the hexa and all, for everything. So make sure, please, to apply this. So here, I'm sorry, the base is 8, not 2. This is the octal. Now there is a programmer joke. They're saying that Christmas equal to Halloween. How? Christmas is December 25. Halloween is octal 38. So let's try to convert octal 38 to decimal. Let's see. You can convert it in two ways. You can convert this to binary and binary to hexa. Or you can make the base, which is 30 base 8. 31 base 8 is going to be 3 times 8 power 1. This is B1, B0. Plus 1 times 8 power 0. So 3 times 8, 24. Plus 8 times 8 power 0, 1. 24 plus 1 equals 25. This is the base 10. So decimal 25 equal to octal 31st. Or you can convert this to binary. So we will say that 38 base 8. Now 3 is 3 digits. So the 3 here is 0, 1, 1. So it's going to be 0, 1, 1. Now 1 is actually 0, 0, 0, 1. 0, 0, 1. This is in binary. Now convert this to decimal, which is going to be, you don't need to worry about this 0 because it will be 0. Then 1, 1, 0, 1, 0, 0, 1. This is base 0, base 1, base 2, base 3, or bit 4. Well, it should be bit, not base. I don't know why I call it base. So it's going to be 1 times 2 power 0 plus, or let me start from write the bits. B4 times 2 power 4 plus P3 times 2 power 3 plus P2 times 2 power 2 plus B1 times 2 power 1 plus B0 times 2 power 0. Then B4 is 1 times 2 power 4, which is, I think, 16. B3 is 1 times 2 power 3, which is 8. B2 is 0 times 2 power 2, which is 4, plus B1 is 0 times 2, plus 1 times 1. Then it's going to be 16, plus 8, plus 0, plus 0, plus 1. So 8 plus 16 is 24, plus 1, 25. Decimal. Clear? Any questions? Okay. So now the question, when 1 plus 1 equal 10? Binary, right. This is also another joke of the programming. 1 plus 1 equals 10. Okay, so that's what you need to know. Basically, in summary, when we have decimal, we know how to convert it to binary and the vice versa. Then you can convert it to octal or hexadecimal. Sometimes converting from octal to decimal can be done in this way, times 8 power 1 or 8 power 0. And the same for hexa, times 16 power 1, 16 power 0. This can be done in an easy way, or you can follow the binary rules. So you need to know how to make the conversion between all of these 4 systems, so including the decimal point, if there's a decimal point.